Okay, we'll have a look at October 13, 2013, the last question, question 5. During evening twilight on the 23rd of Jan, we observe Venus bearing 275 gyro, 282 compass. We'll give a DR position and a chronometer reading. We need to find the error of the gyro. The first thing we need to establish is the universal time. We've got the chronometer time showing, but this could be 19 hours 11:42 or 7:11:42. We need to establish which it is. And also we've got 23rd of January as the evening twilight. Well, we need to establish whether in fact it is indeed the 23rd of January. So we go into the 23rd, look up civil twilight at 46 degrees south, which is our position. And we find that it's local time, it's always local time, that is 2018. Let's apply our longitude to find our approximate universal time. So 23rd of January 2018, longitude comes out at 10 hours 50 minutes and it's west, so we have to add it. Therefore our approximate universal time is 0708 on the 24th of January. So you can see this question straight away, it's taken us into the next day. So when we look at our chronometer, we can see it is indeed 7 hours, 7:11:42, and then we apply the correction because our approximate time is 0708. So therefore the correct universal time is 07:12:47 on the 24th of January. All we then do is go into the tables with the time on the 24th, look up the GHA of Venus, increments, V correction. Although there isn't a V correction, we still put it in to indicate that we understand there may well be one to apply. Get the GHA, apply our longitude, that gives us our LHA. Look up the declination of Venus, apply the D correction, get the declination of Venus. Although these D and V corrections make hardly any difference to the answer, it's very important to put them in because it's a principal error if you don't. Then we use the A, B, C formulas. A, tan lat over tan LHA, we get the value, and that's north because our LHA is 77 degrees, 12.3. If you're unsure, of course, it mentions it in the Norris tables. B always named the same as declination, 0.05925 south. Notice how many decimal places I've gone to, 5 there. Because one's north, one's south, we subtract one from the other. That gives us our C correction, 0.17757 north. We then use the tan azimuth formula, 1 over C times cos lat, and of course it's north, and it's west again because of the LHA 77 degrees 12.3, so we get a bearing of north 83 degrees west, which is 277 degrees true. So we now compare that to the bearings we got, 275 gyro and 282 compass. So 275 gyro, it must be 2 degrees low, okay, and we need to find the deviation, and we're told that the variation is 5 degrees east. Variation plus deviation gives us compass error, or variation and deviation combined I should say, rather than, it's not always plus of course. Compass bearing was 282, true bearing 277, therefore I had a compass error of 5 degrees west. So I think the fail-safe way to do this, put variation and deviation together and compass error, because the two make compass error. We know our compass error is 5 west, we know our variation is 5 east, therefore we need to work out what value to put in there. And it must be 10 degrees west, because 5 degrees east less 10 degrees west gives us 5 degrees west. The last part of the question asks us to look at deviation card 4 and state the deviation that you should have expected and any subsequent actions in light of the observation. Okay, and it told us at the time of the observation the ship's head by compass was 040. So we simply go into the tables at 040 and find that we should have expected a deviation of 2 degrees west. Our deviation is 10 degrees west, so what actions do we take? Well, we recheck our calculation straight away, do another compass error, check the compass error book to see how the error has been going. If still in doubt, call the master and go into hand steering.